Hello, everyone, and welcome to our presentation on improved multimodal emotion recognition using squeeze and excitation block in cross-modal attention. I am Jessin James, and Junchan Liu and I are from the Department of Electrical, Computer and Software Engineering at the University of Auckland, New Zealand. And we are also part of the speech research at the University of Auckland Research Group. Our co-author, Dr. Karan Nathwani, is from the Indian Institute of Technology, Jammu, India. Human-computer interaction has gradually integrated into our lives, especially after the advent of COVID into our lives. This has increased the need for contactless interaction, and hence human-computer interaction has become paramount. Now, there's a need in human-computer interaction to analyze and understand emotions from humans, especially from their facial expressions or from speech or from text. Now, even though this is essential, this is also challenging. This is because human emotions are different, because different individuals express emotions differently. Also, the emotions have some subtle differences and they are difficult to separate. For example, happy versus excited, it's quite difficult to draw a border between both of them, and hence it's difficult to express them using specific features. So, recognition of these emotions also become quite challenging. Now, even though it's a challenging problem, there are many solutions to it. In early times, people used to do uni-modal emotion recognition, where we use one modality like face or speech or text and recognize emotions from it. Now, this approach produces low robustness because because of the issues with human emotions. For example, in facial expression-based emotion recognition, issues of face occlusion can come into picture. In speech emotion recognition, factors such as environmental noise and pitch changes can be a factor. In text-based emotion recognition also becomes difficult when people use the same word to express different meanings. So a multimodal emotion recognition is much better because it produces robustness and data complementarity. Due to the fact that we have multiple modalities to make a decision, reduces the impact of having similarity between emotions and also reduces chances of making mistakes in emotion recognition. So with that in mind, we have developed a multimodal emotion recognition system with the two main contributions. The first one is that we have leveraged the impact or leveraged the use of new neural network based systems such as BERT, ResNet, and DenseNet for feature extraction of text, speech, and video, respectively, thereby capturing vital information about emotions. Also, we have introduced the SE block, which is a squeeze and excitation block into cross-modal attention to ensure that multimodal interactions are captured and also improve feature representations. Now, these two contributions have been tested on two databases. The first one is the IMOCAP database, which has the emotions that are shown on screen, but it's an unbalanced data set. To make this data set balanced, it's common for people to remove certain emotions to ensure that the database is balanced. Now, the other database that we have tested on is the RAVDIS database. Now, this is a balanced database and has the emotions that are shown in the screen. Now, let's look at the methodology. The proposed system uses three modalities. One is text, the speech signal, and the video. Now, for the text modality, we need to first do a feature representation of it. For that, we have used BERT. Now, BERT is a well-known pre-trained model and has been very successful in text classification, question answering, and dialogue generation. We use BERT in our work due to its bidirectionality, allowing it to comprehend word meanings and word meanings and semantics within the entire sentence context, which is quite useful when you're doing emotion recognition. For audio or the speech signal, a MEL spectrogram of the speech signal was captured. Now, MEL spectrogram captures frequency and temporal characteristics of the speech signal as an image, as you can see in the diagram. Now, emotions in speech are often conveyed by changes in pitch, intensity, and timing, and MEL spectrogram captures all of it. Now, once you have a MEL spectrogram, you have an image of the speech signal. Now, this image can then be converted into features by using different approaches, and we have chosen ResNet. Now, ResNet is quite useful because ResNet skip connections enable us to capture hierarchical features at different levels of abstraction from the MEL spectrogram. Now, for the video modality, instead of taking the entire picture, we have only captured the face. Now, face is an image. Now, features of the face were captured using DenseNet. Now, DenseNet is also a very useful network for video feature extraction due to its ability to promote gradient flow and feature reuse through dense connections between the neural network layers. This alleviates vanishing gradient and network degradation issues. DenseNet also captures and utilizes multi-level emotion features, including both local and global semantic features, thereby making it a good choice for emotion recognition. After all the features are extracted as seen in the figure, we have then gone and used an encoder block that consists of 1D CNN and BiLSTM, and this is used to capture the temporal and contextual information from the sequential input for emotion recognition. BiLSTM is quite useful because it has a complex gating mechanism, and that makes it possible to learn long-term feature dependence, enhancing emotion model performance. Given these reasons, we have used BiLSTM to extract temporal information in our proposed model. Now, after this, the rest of the methodology will be explained by Junchen Liu in the remaining part of the presentation.
Thanks for Jason. I'll introduce the next section. Our proposed model utilizes a unique feature fusion approach that combines cross-modal attention with the inclusion of squeeze and excitation block. Regarding the cross-modal attention, it solves the problem that traditional feature fusion methods often fail to utilize the correlation between modalities. Cross-modal attention enables the model to adaptively learn interaction and the dependence between modalities. By allocating the weights to feature based on their contributions, cross-modal attention integrates information from multiple modalities. The cross-modal attention comprises the multi-header attention layers, where each multi-header attention layer takes input in the form of a query, the key, and the value matrices. These matrices are projected into the H subset through the linear transformations, with H representing the number of heads. This specific projection process is described in these three equations. The attention operation in each subset is calculated as equation 4. For multi-header attention modules, the feature from one modality acts as a Q, while another modality serves as K and V. In cross-modal attention model, we perform 6 multi-header attentions to capture correlation between different modalities. Finally, concatenate the 6 output obtained from the cross-modal attention to gain the feature that contain the 3 modalities interaction information. The second part in feature fusion method is squeeze and excitation block. IC block is typically employed in computer vision applications such as image classification and object detection. It serves the purpose of channel-wise feature recalibration, enhancing the representation power of individual feature maps. Although the IC block is not a direct feature fusion method, we chose to incorporate for the feature fusion due to its ability to selectively enhance the relevant information within each modality feature by assigning different weights to channels. This indirectly reduced the impact of feature containing reductive information on the model, and an IC block enhanced the feature distinctiveness by assigning weights to different features, making the model more sensitive to subtle emotional changes and improving the generalization capability. To the best of our knowledge, the IC block has seldom been used, and hence attempted in this paper to achieve robust multimodal emotional recognition. IC block comprises 2 operations, namely squeeze and excitation. The former reduces the spatial dimensions of the input feature maps to a single value per channel by using global average pooling, The input feature U is the output from the cross-modal attention with the size Y times C times D, where C refers to the number of channels and D is the dimension of the feature. Squeeze operation could be calculated as the equation 5. Excitation meaning adjust each channel's feature response through the learned weights. Excitation contained to the fully connected layers with the weights metric W1 and W2 in equation 6. The delta refers to the Rayleigh function and the sigma refers to the sigmoid function. In equation 7, F-scale in channel-wise multiplication between UC and SC and the output of S block X consists of X1 to Xc, which has a similar size with the input. So before the classification, we apply the statistical polling layers. Statistical polling is a novel type of a polling layer. It calculates and combines both standard deviation and the mean of the input. The standard deviation in statistical polling captures temporal feature representation. By summarizing the first feature using statistical measures, it provides a representation that incorporates information from multiple modalities. Hence, applying statistical polling is a suitable choice when dealing with multimodal information. This is a statistical polling equation where X is the output of SE block. In summary, our proposed model utilizes the deep learning method for emotion recognition. Our objective is to utilize the bidirectionality of BERT to capture the meaning and the semantic of words in the context of the sentence and extract emotional information from the text. In addition, we use the reset to capturing and utilizing the time dependence email spectrograms. For videos, we use a densite which can extract emotional information from face and different scales and angles to find the correlation between modalities and enhance the feature representation. We incorporate cross-modal attention as a block. This component determines the generalization of multimodal emotion recognition model. So let's see the result. We compare our proposed method with other method by using the mocap and the Ravadas dataset. For models that are only evaluated in the mocap dataset, due to the fact that the mocap is an unbalanced dataset, even with different models, we can observe that the unweighted accuracy of the model gradually decreases as the number of classes increases, highlighting the challenge posed by imbalanced sample set in the mocap dataset. But it is worth noting that our proposed model achieved a remarkable 79.2% unweighted accuracy even with 7 classes. And we compare models that only use the Ravadas datasets. Our proposed model got the highest accuracy. And we conduct an experiment on different combination of modalities to evaluate the performance of our proposed model on the 7-class mocap dataset. And they are evaluated using the 2 criteria, weighted accuracy and unweighted accuracy. The results are summarized in Table 2. Among the 2 modalities models, the combination of speech and video modalities achieved the highest performance with a weighted accuracy of 74.2% and unweighted accuracy of 78.8%. To access the impact of SE block, we provide confusion matrices for our proposed model with and without SE block on a mocap dataset. With the inclusion of the SE block, we observe a reduction in the number of utterances predicted excitement inside the happiness, and the accuracy of prediction for the happiness and sad has improved. The enhanced performance can be attributed to the SE block's ability to improve the feature representation by assigning different weights to each feature channel. This reduces the negative impact on reducing information from the modalities and enhances the model's ability to capture subtle distinctions between emotions. These 2 figures illustrate the loss and accuracy curves of our proposed model on the mocap dataset. The loss curve exhibits initial fluctuations during training, but stabilizes after the 20th box. Both the weighted accuracy and unweighted accuracies show improvement and reach their peak value during this period. So in conclusion, our proposed multimodal emotion recognition model addresses the challenges of emotion recognition tasks by leveraging text, audio, and video modalities it achieves impressive performance even on unbalanced datasets. The result obtained on a mocap and a Ravadas dataset highlight the strong feature extraction capability of a BERT, RedSet, and DenseNet, and the combination of cross-modal attention and SD block enables effective computation of correlation between modalities and enhance the model's ability to distinguish the subtle difference between emotions. So in future research, we will use attention maps to understand which part of the feature the model focuses on when making decisions, and finding the model to improve the model's performance in multimodal emotion recognition tasks. Thank you. Hope you enjoy this presentation.